Networking with automata, the finite frontier. Today we'll be learning about what a finite automata is and how it is used in networks and how significant it is in it. We'll also brief upon the types of finite automatas. Along with that, we'll also discuss about the challenges faced by finite automatas and the future ideas for it. We'll also brief on the case studies done by industry-leading companies like Google and Cisco on finite automatas usage in networks. Let's go for the next one. Introduction to finite automata. Today we'll explore one of the fundamental concepts in computer science and mathematics, which has wide-ranging applications in fields such as software engineering, artificial intelligence, cryptography, and of course networks. At its core, finite automata is a mathematical model used to represent a machine that reads and processes inputs. It is a finite set of states, transition between states, and an initial and state that receives input symbols from a finite alphabet. The machine transitions from one state to another, following the rules defined by the transitions, and ultimately accepting or rejecting it, the input state. Understanding finite automata is crucial for designing efficient algorithms, verifying software correctness, building computational models. We'll dwell into various types of finite automata, such as deterministic finite automata and non-deterministic finite automata, and learn about them. We'll also see where it's used in networks in the next few slides. Basic components of finite automata. The fundamental components of finite automata include states, transition, and input symbols. A state is a condition or mode of system that can change in response to the input symbols. Transitions are the links between states that show the possible changes in the system. Input symbols are the alphabet of strings that can trigger transition from between states. There are two types of states in finite automata, initial states and final states. The initial state is where the system begins and the final state is where the system ends after processing the total input symbols. Finite automata can also have multiple inputs and outputs, allowing them to solve more complex problems. By understanding the basics of components in finite automata, we can create more powerful and efficient models to understand and solve the real world problems. In conclusion, the components of finite automata are essential building blocks that allow us to create mathematical models to solve complex problems. By mastering these fundamental concepts, we can create more efficient and effective solutions to all those problems. Now let's discuss about the types of finite automata. There are two main types of finite automata, the DFA deterministic finite automata and NFA, the non-deterministic finite automata. The first type is DFA, which has a fixed number of states and accepts or rejects strings based on its current state and the input it receives. The second type is NFA, which can be in multiple states at once and accepts or rejects strings based on all the possible states and the input combinations. As discussed in the previous slide, the first type is DFA. A DFA can be represented as a directed graph pictorial, where the vertices represent the states and the edges represent the transition between the states based on the input symbol. When the input string is fed into the DFA, it transitions from the state to state until it reaches either an accepting state or a rejecting state. That is, we have to get results. It either has to pass the thing and it should just get rejected. One of the advantages of a DFA is that it can recognize a language in linear time, making it an efficient tool for pattern recognition, and moreover, it is easy to implement and understand compared to the other models. A DFA has many applications, including compiler design, natural language processing, and regular expression matching. It is also used in network security to recognize patterns in the network traffic and detect attacks. In conclusion, DFA is the most powerful and efficient model for pattern recognition. By understanding its properties and capabilities, we can develop more efficient algorithms and advance our understanding on computation. The second type of FA is NFA, non-deterministic finite automata. The NFA is a type of finite automata which differs from DFA because it exists in multiple states at once. This feature makes NFA more powerful than DFA, but also makes it more complex. An NFA is defined by a set of states, a set of input symbols, a transition function, a start state, and a set of substates. Unlike DFA, an NFA can have multiple possible next states for a given input symbol. When the NFA receives an input signal, it can explore all the possible paths simultaneously, which makes it a much more powerful tool naturally. While NFA is more expressive than DFA, it can be more difficult to work with and implement. However, there are algorithms available to convert NFA to DFA, which can simplify the overall process and makes it much easier to work with. Non-deterministic finite automata are a powerful tool for recognizing pattern in strings of characters. Their ability to explore multiple paths simultaneously makes it well suited for using in applications such as natural language processing and parsing. Finite automata in networking. In networking, finite automata are used to model the behavior of network protocols. Briefly, network protocols are a set of rules that govern how data is transmitted over a network. These protocols have a finite number of states, and the behavior of the protocol depends on which state it is in. By modeling these protocols using finite automata, we can better understand how they behave and how to make improvements to them. Finite automata are used in network security, network monitoring, load balancing, pattern matching, protocol implementation, and packet processing. For example, we use finite automata to detect patterns of behavior that may indicate an attack on the network. By detecting these patterns early, network administrator can take steps to prevent the attack from being successful. Finite automata play an important role in networking, both in modeling and behavior of network protocols and in network security. By understanding how these models work, we can improve the overall performance and efficiency and also the security of our network. The regular expressions for pattern matching. A finite automata can recognize patterns in strings of characters. Regular expression can be translated into finite automata to perform matching efficiently. Finite automata work by processing one character at a time and transition between states based on the current input. They can recognize a wide range of patterns, including simple ones like sequence of characters to more complex ones like nested parentheses. By using regular expression to generate a finite automata, we can efficiently search for patterns in large amount of text. This technique is widely used in programming languages and text editors to implement regular expression functionality. In conclusion, the combination of regular expression and finite automata is a powerful tool for pattern matching in text. It allows us to efficiently search for patterns in large amount of text, making it an invaluable tool for developers. Composing finite automata for complex behaviors. Just as the definition goes, the finite automata are mathematical models that can represent a simple and complex systems with a finite number of states. By breaking down complex behavior into simple components and modeling them as finite automata, we can achieve a more efficient and effective solutions. Composing the finite automata enables us to create more sophisticated and adaptable systems that can respond to changing environments. It allows us to better understand the underlying structure and behavior of the complex systems. By utilizing this tool, we can design and develop systems that are more flexible, robust, and capable of handling a wide range of situations. In short, complex situations. Application of finite automata in network security. Finite automata can be used in network security to detect and prevent attacks on day-to-day basis. One of the main applications of finite automata in network security is intrusion detection. By modeling the behavior of legitimate users and network devices, finite automata can detect anomalies and potential threats in real life. For example, a finite automata can be trained to recognize patterns in network traffic and flag any unusual activity that deviates from the established norms. Finite automata can also be used to create firewall rules that filter and block unauthorized traffic by defining the permissive input and output of network devices by using finite automata. Network administrators can ensure that only legitimate traffic is allowed through the network. This helps to prevent denial of service attacks, port scanning, and other malicious activities. Furthermore, finite automata can be used to implement access control policies that restrict the actions of unauthorized users. By modeling the actions and privileges of different users using finite automata, network administrator can enforce granular access control policies that prevent unauthorized access to sensitive data and systems. An application of finite automata and network security is a powerful tool that can help organizations to detect and prevent potential threats in real time. By modeling the behavior of legitimate users and devices, a finite automata can create a safe and secure environment that protects the system from cyber attacks. Finite automata in network routing. In the context of network routing, finite automata can be used to efficiently route data packets from their source to their destination. By representing the network topology as a finite automata, routing algorithms can use the state transitions to determine the optimal path for a given packet. This approach has proven to be effective in both traditional wired networks and modern wireless networks. where the limited bandwidth and high mobility of devices require efficient and adaptive routing algorithms. Hence, the use of finite automata in network routing is a crucial aspect of modern networking technology. By leveraging this mathematical tool, we can ensure that the data packets are delivered in timely and efficient manner, enabling the seamless flow of information across the network. Design and analysis of finite automata for networking. The analysis of finite automata is crucial in networking because it helps us to ensure that the protocols we design are efficient and reliable. It allows us to test our designs and identify potential problems before they occur, which can save us time and resources. There are few standard methods for designing and optimizing finite automata in networking. They are minimization of FSMs to reduce complexity and memory usage. This means we have to minimize the FSM just to save our resources. For example, a 5-state FSM can be reduced to 3-state one if it's the most least thing. Hence, we reduce the memory usage. The next one is composing multiple FSMs to create complex behaviors. This is done to cater to complex problems such as traffic shaping, load balancing, etc. The next one is formal verification of protocol statements to ensure correctness and security. In FSM, there will be like no errors. So once a program runs, we are going to get some output, and to ensure that it's correct, we have to verify it. That's what this rule states. Challenges in using finite automata in networking. Using finite automata in networking comes with several challenges. One of the primary challenges is the complexity of network protocols. Network protocols are becoming more complex, and designing finite automata to model them is becoming increasingly difficult. Another challenge is the dynamic nature of networking environments. Networks are dynamic, and network protocols must adapt to changing conditions. Designing finite automata that can adapt to changing conditions in real time is challenging. Finally, scaling finite automata to handle large networks is also a challenge. As the size of network grows, the number of states in the finite automata increases, making it difficult to analyze and manage the overall system. So, while finite automata are useful tools for analyzing network protocols, their application in networking comes with significant challenges. Addressing these challenges will require innovative solutions and deep understanding of network protocols and their behavior. Case studies. There are several case studies that shows how these powerful tools can be used to create efficient and reliable networks. Few top companies like Google and Cisco use FSMs for their day-to-day activity. Google use FSMs for load balancing in their data centers, and Cisco use FSMs for deep packet inspection in their firewalls. All these shows nothing but the insane potential the FSMs have in the networking industry and guarantees their future. Coming to the last slide of the presentation, I would like to discuss about the future of the finite automata in networking. Finite automata, also known as state machines, have been widely used in networking protocols for decades. However, as networking technology continues to evolve, the role of finite automata is also changing. In the future, we can expect to see even more advanced and sophisticated finite automata being developed to handle increasingly complex networking tasks. These automata will be able to adapt to changing networking conditions, learn from the past experience, and make more intelligent decisions. Moreover, finite automata will continue to be a critical component of network security, helping to detect and prevent cyber attacks as the number of and the as the number and the complexity of cyber threats continue to increase. The ability of finite automata to quickly identify and respond to these threats will become even more important. In conclusion, while the role of finite automata in networking may evolve, the importance in ensuring stability and security of our networks will only continue to grow. We can look forward to exciting advancements in the field in the years to come. Thank you.